Okay, hello everyone. Let us start with today's topic, uh, that is basically discrete time convolution, and we had already done continuous time convolution in LTI systems, and today we would be doing the same thing for the discrete systems. So we have today's topic is discrete time convolution. So as we had done in the last class, we had seen that the basic meaning of convolution is actually the uh, overlap of one signal over the other signal. That is basically what we mean by convolution. Actually, it is a mathematical tool to identify the overlap that one signal is having over the other signal. So essentially, we have two signals, and we know that we had taken two signals as one of the signals were the input signal, and the other signal that we had taken was the impulse response, and then we had taken the output signal. So yesterday what we were doing was in the continuous time. Today what we will be doing is in the discrete time. So in the discrete time, as you know, that the time parameter, the discrete time parameter is denoted by n. So xn is the input to this LTI system, or basically in a better manner, we call it as a linear shift invariant system, LSI system. So this is an LSI system, and h of n is the impulse response of that LSI system, and the output of the system is y of n. So y of n will be obtained as the convolution between the input signal and the impulse response. Now, in the discrete sense, what happens is, we know that the integration that becomes summation, and this summation varies from there. The limits were over tau. Here we define another parameter, that is k, and k varies from minus infinity to plus infinity. The tau was varying from minus infinity to infinity. Okay, I'll write down the expression for continuous time also to so that it becomes better. It becomes easier for us to make the analogy here. So we have x of t convoluting with h of t that we had written, if you remember, that was integration from minus infinity to infinity, and the convolution between x of t and h of t. So that was basically, we replace it as x of tau and h of t minus tau d tau. So basically we had seen that there was a shift and scaling and these things that were happening in this function, that was our impulse response. So the same kind of, and this one, our input was fixed. This was basically fixed, what we had discussed in the last class, and here we were performing operations like shifting and then the scaling. Scaling was essentially about time reversal that we had discussed. So scaling was essentially about time reversal, and then we were essentially multiplying both of them and so on. So essentially these operations were done, we'll again recall, so that we are able to overlap h of t minus tau. This essentially, this is h of tau, to overlap or to slide this h of tau over x of tau. Okay, so that was what we had done. Now here in case of discrete system, our n translates to k. We basically, what we do here in discrete time system, that the first step that we follow is that we change this n to k. So this becomes x of k, and here we have h of basically n minus k. We'll see how it is happening. The same thing what we were happening here. What was happening here? First we had changed this to this t to tau and this to h of t to h tau. Then we performed time reversal here, and then we did minus of tau minus t here. This was what we had done. The same thing we are going to do here also. Okay, so we can see that the first thing that we wanted to show here was the expression that we write for discrete time convolution. So discrete time convolution can be written with this expression that basically represents the, this expression basically represents a discrete time convolution. So now essentially what is happening that we'll see that we had already seen in the case of continuous time, and now we will be seeing that in the case of discrete time. So we have two signals in the discrete form. We have two discrete time signals. The first signal is x of n. The second signal is h of n. Okay. Now, if you remember, in the last class, we had said that basically convolution is a mathematical tool to identify, to calculate the overlap of one signal when it slides over the other signal. Okay. So to check this particular operation, to make this particular operation happening, the first thing that we do is that we replace this n with a dummy variable k in exactly the same manner as we had done in the continuous time, where we had replaced the parameter t with a parameter tau. Okay, that this is what we had done. And then we have what we had done. We had fixed this particular one signal that we have fixed in the continuous time. So here also we will fix it. We fix it. And then what we do, we basically perform the time reversal here. We basically perform the time reversal. So when we perform time reversal, what happens? This becomes h of minus k. The next thing that we do here is we perform time shifting. We perform time shifting, and we essentially shift this signal by n time units, so that it becomes h of n minus k. Okay, and then what we do? We do multiplication. In the next step, we do multiplication, where we multiply this h of n minus k with x of k in the manner similar to the continuous time case, where we had multiplied h of t minus tau with x of tau. So here we are going to multiply h of n minus k with x of k. This multiplication we perform, and the last step, in the last step, here we had done integration. Here we are going to do summation, because in the discrete time case, whenever we change a particular function from the continuous to discrete time, integration essentially maps to summation, and we get here our summation of x of k, h of n minus k, and k varies from minus infinity to infinity in the similar manner, like here tau was varying from minus infinity to infinity. Now our k will vary from minus infinity to infinity. These are the steps that we perform to do convolution in discrete time signals and systems. Okay, so let us start with to understand this better and to get better insight into what we are discussing here. Let us start doing an example. Now this time we'll take, let us say that we have our input signal as a unit step signal, and our transfer function, that is also a unit step signal. We have this kind of system, so, and we have to calculate y of n. What is y of n? Okay, essentially we have this x of n is given as input to a linear shift invariant system, where h of n is the impulse response, and the output that is produced as y of n. X of n is unit step signal h of n is also unit step signal, and we have to calculate y of n. We'll see that what will be the value of y of n, and as we know that in a linear shift invariant system, we have to perform the convolution between these two, the input and the impulse response. So when we perform convolution between x of n and h of n, essentially we have to do the convolution between u of n and u of n. Okay, this is our y of n. Since y of n is nothing but the convolution between x of n and h of n. So we start with this. So the first thing that we do here now, okay, the first thing that we do here, as we know that we have u of n. So the first thing that we'll do is here is we change this n to k. So we make both of them as u of k. Now the two signals that we are having, straight line, got a better. Okay. Now, how does a unit step signal look like? We know it looks like something like this. Probably for the unequal lines. So with k, this u of k varies in this manner. So we have to perform this u of k. This is the first function, the function number 1, or the signal number 1, this one. And then we have the second signal. So our second signal, again, that is also here. Anyway, this is a straight line again. So this kind of signal that we have as our second signal, and this is varying with k only. Okay. Now what we have to do? We have to perform time reversal here now. So that is u of minus k. That is what we have to do now. So what will be the time reverse signal? Time reverse signal will look like, we have this. And so on. This is our u of minus k. This is the time reverse signal. Okay. Now the third case is that when we perform the shifting. Okay. So when we perform the shifting, as you know that what we do essentially, whether this was the first operation, this was the second operation, the third operation I'm writing here. Okay. This is the don't confuse it with the first signal and second signal. Okay, this is the first operation. I'll write here like this. This is the second operation, and now I'm writing the third operation. So the third operation is shifting operation. And how do we do the shifting? So we have this minus of k is here. We essentially delay this particular time reverse signal by n units. And as we had discussed in the last class, that we are delaying it by some time units. Now it depends on the positivity or the negativity of this parameter n or t, whatever it is, in the continuous time if we are taking t, or in the discrete time we are taking n. So it depends on the positivity or negativity of this n or k, whatever we are taking, basically, that whether our this time reverse signal is shifting in which direction? Basically, it is getting delayed or it is getting advanced. So in this case also, you can see that if I say that, if I define a case number 1, where n is less than 0, I say that n is less than 0, which means that n in the discrete sense, it becomes n is less than or equal to -1. Okay, so n is less than or equal to -1, you can see here. So in that case, what is going to happen? So a typical, this essentially becomes u of n minus k, and if I want to draw u of n minus k here, so we can say that, you can see here that u of n minus k will look something like this. Will look something like this, and where we have basically this value here, this is going to be n. Suppose I have taken n as equal to -1, so this is going to be -1 only. If I'm taking, because it is getting shifted by that value, we are basically taking u of minus k minus n. So for example, let's say that I say, for example, let's say that I say n is equal to -2, let us say. So what this will become is, this will become u of minus of k plus 2. Okay, which means that basically what we are doing, we are advancing it. So whatever value we take for n, whatever negative value we take for n, in this case, it will be advanced in that manner. So whatever value we take for n, these samples will start from there, and u of n minus k will look like the way it is shown in this figure. And then the next thing what we have to do is, basically we have to multiply this one and our first signal u of k, that is our fixed signal. So if we multiply here, you can clearly see that if I multiply u of k and u of n minus k, okay, so what I'll do is that I'll show u of k, I'll show with red, and u of n minus k I'll show with blue. Okay, so now how will our u of k look like? So our u of k will be over this one and this. Okay. This and this and this and so on. This will be our u of k. And how will our u of n minus k look like? So that I'm going to draw with blue. So that will be like, what can we see in this manner? Okay. This is basically u of n minus k, and this is u of k. If we multiply both of them, you can see that clearly it will be 0, because in this region there is no u of n minus k, and in this region there is no u of k. So this multiplication becomes equal to 0. U of k and u of n minus k becomes equal to 0. So that will be essentially the value of y of n will be equal to 0 for n less than 0. Okay, that was the first case. Now we'll do the second case. Now, like in the first example, in the previous example that we had studied yesterday, that we had discussed yesterday, basically there were two signals that were varying from 0 to 2 and 0 to 1. But here in this case, there are only we are only interested in the case that is n is either greater than 0 or n is less than 0. So last time we were having almost 4 cases, like for t less than 0 and then t greater than 0 but less than 1, and then greater than 1 and less than 2, and then greater than 2 and less than 3. In this manner we were having several cases, and likewise we got 4 cases in that example. But here we'll be having only 2 cases. The first case would be that was what we had already discussed now, that n is less than 0, and the second case is going to be n is greater than 0. This is the second case. So when n will be greater than 0, if I ask that what is going to be u of n minus k, so as we know that u of n minus k is nothing but the delayed version of this time reverse signal. So now we have n is greater than 0 here. We have n greater than 0, any value that is greater than 0. So that means that this is representing a delayed signal. Okay, so this is representing a delayed signal. I'll make this is our u of n minus k, and u of n minus k is going to look like something like, since n is having a positive value, so we'll have this kind of just forgive me for this unequal spacing. I hope you will understand that what is going on. I mean, what's the value and so on. This is going to be our u of n minus k. Okay, where this value here, this is going to be n. And the second signal, the first signal, our first signal. Okay, this is our second signal. That is already delayed and shifted and so on. Now I'll draw the first signal. Our first signal, that is u of k only. So now this u of k is going to have the value the simple manner, as we know that this is going to have this kind of value. Okay, this kind of value we are going to have for u of k. Okay, so now we have to multiply u of n minus k and u of k. So you can see that in this region, that is essentially, I'm sorry, here this k is varying. Essentially, when k is equal to 0 and when k is less than 0, from minus 1 onwards, this is minus 1, minus 2, minus 3, and so on. This is 1, 2, 3, 4, 5, 6, and here also we have 1, 2, 3, and here we have 0, minus 1, minus 2, minus 3, minus 4. So we can see that from, if we look into k is equal to -1, -2, this region, we can see that the product is going to be 0. The product of u of k and u of n minus k is going to be 0. And beyond this n also, this value is basically n. Here, for example, this has become 3. This value is n basically. That is basically the amount by which we have shifted this signal, by which we have delayed this signal, that is n. So that n value is here. So up to n only we will have this product as this multiplied, this 0th sample will be multiplied with the 0th sample. The first sample will be multiplied with this first sample. The second sample will be multiplied with this second sample. So the third sample will be multiplied with this third sample. And then the fourth sample will be multiplied with this fourth sample and it will become 0. So only up to n here, the product of u of k and u of n minus k is going to have some value that is equal to 1. That is u of k multiplied by u of n minus k will be equal to 1 only in the region n equal to 0, okay, k equal to 0, 1, 2, and so on up to n. Okay, only for these samples it is going to have value 1. We'll take one example. Let us say that it will be better to understand with an example. So we have, let us say that n is equal to, let us say 2. I say that this is here, it's 2. Basically, this becomes, here it was actually 3, but let us say, take it as 2 only. So now what will happen? I'll draw both these signals now. Okay, so what will be u of n now? So it will be u of n now. This is, I'm going to draw for n equal to 2. U of this is basically u of n minus k, isn't it? These are all equally spaced, and this is basically u of n minus k. So we have this as 0, 1, 2, and here it is minus 1, this one -2, -3, -4, and so on. This is essentially u of n minus k for the example n is equal to 2. And what will be our u of k? So u of k will be the same u of k which we have seen till now. So we have these are all one values only. This is our u of k. Here also it is having one. And so on. This is our u of k. Now I see here that this is 0, this is 1, this is 2, this is 3, this is 4, 5, and so on. Okay. Now just simply see here. If I multiply u of k and u of n minus k here, what is going to remain? So let us divide this k into some regions now. So let us say that we have like n is equal to 2 we have. Okay, so when if we are having, suppose I say that when we are taking k on the values k less than 0 in this region, okay, that is basically k is less than or equal to -1. Okay, means we are taking values from -1, -2, -3, -4, and so on. Here also I take -1, -2, -3, and so on, all the values. Okay, so when we take the product of these values, So this is what we were discussing. Basically now we have, so if I say that the product between u of n minus k and u of k now. So for k less than 0, we can see that these values are simply, we can see here that 0 only. Okay. And for the region in the positive side, okay, in the positive side, if I see on the positive time axis, we can see that for here at this 0th sample, first sample, and second sample, okay, we will be having values 1. So for k is equal to 0, 1, and 2, we will be having here 1 plus 1 plus 1. Okay, these three will multiply, and that will come out to be 3. And then again for k greater than or equal to 3, we'll again have here this as 0. So in a general case, what we will get here, that this the outcome here, the outcome of this convolution was yn was equal to 3 when n was equal to 2. So for a general system, what we'll have, yn will be equal to n plus 1. Okay, when n is greater than 0, or simply we can say that yn will be equal to n plus 1 u of n. Okay, that is what we will obtain here. So in the general solution, after seeing both these cases, the first case was that when n is less than 0, and the second case is when n is greater than 0. So I take a new page and write the general solution that we are having. So the general solution that we have here, we obtain here is that y of n becomes equal to, when n is less than 0, y of n was 0. When n is greater than 0, okay, n is essentially greater than or equal to 0, because we had taken the case of n equal to 0 also. That time it becomes n plus 1, and thus the convolution between u of n and u of n comes out to be n plus 1 u of n. Okay, which means that when we convolute, you can see here, if I say that this is n plus 1, so what it means is that we will be having, you can see here that we'll be having this y of n will be coming out as, like for the case n is equal to 0, we'll be having here one value. Okay, n is equal to 1, this will be 2 un. For n is equal to 0, this will be having 1. N is equal to 1, this will be having 2. For n is equal to 2, this will be having 3. For n is equal to 3, this will be having 4. For n is equal to 4, this will be having 5. And so on. This is essentially n, and this is essentially y of n. So we have here 1, here it is 2, here it is 3, here it is 4, here it is 5. When n was equal to 0, then n is equal to 1, n equal to 2, n equal to 3, this is 4, and n equal to 4, that time y of n is 5. This is happening when this is essentially the convolution between, freehand diagram, then this is a convolution between when y of n is a convolution between u of n and u of n. This is n, this is n, this is u of n, and this is u of n. When we are convolving these two, so we obtain this particular signal. Here we have y of n is equal to convolution between u of n and convolutes with u of n. What we saw essentially was that we had shifted this particular signal. We were sliding this particular signal on the first signal. The first signal was fixed and this signal was slided over this signal, and we are seeing the amount of overlap. So you can see that initially this signal, when it was totally shifted on the negative side, initially for the case that n is less than 0, when it was made u of n minus k, and when it was made u of n minus k, and then it was put totally on the left side. So there was no overlap between the signal and the first signal. There was no overlap between the signal and the first signal. Gradually, when this was shifted towards the right side, okay, gradually when it is shifted towards the right side, see, this is going towards the right side, and then we say that we see that how much is the overlap of this signal with the u of k signal, this signal. So we see that the overlap gradually goes on increasing as we go on shifting it to the right side, as we go on shifting it more and more and more and more to the right side. This overlap over this signal also goes on increasing, and therefore we are getting this y of n goes on increasing, 2, 3, 4, 5, 6, 7. This goes on increasing. This increase shows the increase shows the increase in the overlap of, let's say, h of n over x of n, where both of them happen to be unit step signal only. Both of them are unit step signal only. Okay, that is essentially what is happening. So we stop here, and we'll be discussing a few more topics in the next lecture. Thank you, everyone.